Hi dear students, hope you are all fine. So this is the second video on the chapter Moving Charges and Magnetism. In the last video we have discussed Oersted experiment and concept of Lorentz force. Okay. Now today's video we will start with two problems based on the concept of Lorentz force, and then we will proceed with the topic of force on a current carrying conductor placed in a magnetic field. Okay. We will deduce the expression for the force. So first, these two questions based on Lorentz force. So the first question is, the charge plus q moves with velocity, this velocity v equal to 3I cap plus 4j cap plus k cap meter per second in an electromagnetic field, that is a field having electric field and magnetic field. Value of electric field is given E equal to 3I cap plus j cap plus 2k cap Newton per Coulomb, and this is the magnetic field D is equal to I cap plus j cap minus 3k cap. Okay, Tesla. Magnetic field unit is Tesla. Okay, so electric field and magnetic field is given, velocity is given, charge is plus q. The y component of the force experienced by the charge is. So these are the four options. Okay, so you may pause the video and try this question on your own, and then you can verify. Okay, with my solution. So now see this charge. This charge is moving in electric field and magnetic field. So it is going to experience force due to electric field and due to magnetic field. So we know that expression for force, it is force due to electric field plus force due to magnetic field. Now force due to electric field, this is QE, and force due to magnetic field, this force is called magnetic Lorentz force. So this is Q V cross B. Okay, so I can write this as F is equal to Q E plus V cross B. Okay, now all these quantities are already given. Okay, so now substituting the values, this is F is equal to Q, E is 3I cap plus j cap plus 2k cap plus V cross B. So this is 3I cap plus 4j cap plus k cap, and cross B. So this is I cap plus j cap minus 3k cap. Okay, so now you have to take the cross product of these two terms and then add with this. Okay, now here the question is you have to find the y component of force. Okay, so here you have to find a term that is q times the quantity with j cap, because that is the y component of force, because this force can be written as fx I cap plus fy j cap plus fz k cap, and this is equal to this entire quantity. Okay, so y component of force means you have to equate the j cap term. So if you simplify this, here you will get 11 q 11 j cap. So this, if we equate, so fy, it is equal to 11 q. So that means 11 q is the y component of the force. So among the given option 2 is the correct answer. Achha, next we have this question. The acceleration of an electron at certain moment in a magnetic field, this is the value of the magnetic field, 2I cap plus 3j cap plus 4k cap Tesla, is A equal to xi cap plus j cap minus k cap. Find x. Okay, so if the charge particle, this electron, it is moving in this magnetic field, acceleration is this, and no other information is given, and you are asked to find the value of x. So see, here the charge particle is moving only in magnetic field, so we have to think about only about magnetic Lorentz force. So that is given by F is equal to Q V cross B. So this is the expression for magnetic Lorentz force, that is charge particle is experiencing a force due to magnetic field only. Achha. Now if you see this expression, see force is perpendicular to velocity and force is also perpendicular to strength of magnetic field. This is the basic concept of cross product. Now force is perpendicular to magnetic field. This implies acceleration is perpendicular to magnetic field, because force and acceleration, they will be in same direction. So if acceleration is perpendicular to magnetic field, so that means dot product of acceleration and magnetic field, it will be 0. Dot product of acceleration and magnetic field, it will be 0. So we have to take the dot product of these two quantities. So this is 2x plus 3 minus 4 is equal to 0. Dot product is 0. So this is 2x is equal to 1, or x is equal to 0.5. X is equal to 0.5. Okay, so this is the value of x. Okay, so this is one important property. Like, see, force is perpendicular to magnetic field, so acceleration is also perpendicular to magnetic field. So since acceleration is perpendicular to magnetic field, dot product of acceleration and magnetic field will be 0. Okay, this is the concept. Okay, so I hope these two questions are clear to you. So next we will see magnetic force on a current carrying conductor in a magnetic field. Okay, now see, what is the reason for studying this topic is, see, we have seen that if a charged particle, suppose this is a charged particle Q, okay, and if the charged particle moves in this direction with velocity v, okay, and this is the direction of the magnetic field, okay. So this charged particle is going to experience a force. Okay, suppose this is in this plane. Suppose this is x-axis, this is y-axis. Okay, so charged particle is moving in xy plane. Okay, so this charged particle will experience a force in this direction, given by the magnetic Lorentz force F, and this is equal to Q v cross b. So direction of F is perpendicular to the plane containing v and b. Okay, this angle is theta. Theta is the angle between v and b. So magnitude of this force I can write as QVB sine theta, but theta is the angle between v and b. This we have seen. So that means charged particle, if it is moving in a magnetic field, charged particle, if it is moving in a magnetic field, it is going to experience a force that we have seen. Now a current carrying conductor, there in a conductor we have a conductor where there is a flow of current. That means there is a flow of charges, correct? So now if this conductor is under the influence of a magnetic field, that means these electrons are under the influence of a magnetic field. So if the electrons are experiencing a force due to the magnetic field, that means the conductor will experience a force. Okay, so that is the logic behind studying this topic. Okay, of course we have to study this topic because it is given in NCERT, but the reason, study with proper reason, this is the reason. Okay, so suppose we have a conductor. Suppose this is a conductor. Okay, so this conductor is carrying current. So here I current is coming, so this is current I. Okay, now suppose magnetic field is perpendicular to the plane of the board and it is directed inward. Okay, it is going inward. So inward field will be represented by a cross. Okay, this is magnetic field. This cross means inward. Okay, and if it is a dot means outward. Okay, this is a outward. It is not necessary that we are going to use this symbol only for magnetic field. Even for current you can use. Okay, if the current is flowing inward, so if I am writing here I, so that means current is going inward. Okay, cross means inward, dot means outward. Why? Because see, if we draw an arrow like this is the arrow. So if the arrow is going away from you, okay, so this is the arrow, and if the arrow is going away from you, going inward, so you will see this cross. If the arrow is coming outward, you will see the dot. That is a dot. Outward means dot, inward means cross. Okay, so that is a notation we are going to use. This is a standard notation. Okay. Now magnetic field is directed inward. Suppose this conductor, it has length L and cross section area A. L is the length, A is the cross section area. Okay. Now number of free electrons number of free electrons per unit volume. Per unit volume. So suppose it is small n. Okay. What is the total volume? Volume of this. Volume of this will be how much? Volume is area into length. So that is A into N. So if total number of free electrons per unit volume is N, what is the total number of free electrons in this conductor? Total number of free electrons, it will be equal to N times Al. So this is N times Al. Okay. Now expression for force is Q times V cross B. This is the expression for force. So I can write force. See, this is Q is the charge. This is the number of electrons. So total charge will be number of electrons multiplied by the charge. So F, it is equal to Q is NALE V. Now these electrons are moving with drift velocity. So this is VD cross B. VD cross B. B is the strength of the magnetic field. Now this quantity NAE VD, current, strength of current is NAE VD. This is the strength of current. This is the relation between current and drift velocity. We have already derived this expression in the chapter current electricity. So this NAEVD can be replaced by I. So I can write this expression as F is equal to IL cross B. IL cross B. Okay, so here I have not written the symbol. See, L is without any vector symbol, but while writing IL, I have used a vector symbol above L. Okay, now this L vector, that means it is having a direction. Okay, how to mark the direction? The direction of L vector will be in the direction of flow of current. Like in this case, current is flowing in this direction, so L vector will be in this direction. Okay, so this is the direction of L vector. And what is the direction of magnetic field? It is in the inward direction. Okay, so current is flowing in this direction. Current is flowing in this direction. Magnetic field is in this direction. So if we use right hand curl rule, that is the product rule, cross product rule, IL cross B is force. So this is the direction of IL cross B. So force will be in the downward direction. So force on this conductor, if magnetic field is going inward, current is flowing in this direction, so force will be in downward direction. Okay, this is the direction of the force, and this is the way of representation of force on a current carrying conductor placed in magnetic field. Achha, here you should also learn one more method to find the direction of the force, that is by using Fleming's left hand rule. Fleming's left hand rule. Now Fleming's left hand rule says that if you stretch the thumb, the forefinger and the central finger, this is the thumb, this is the forefinger, central finger of your left hand, in three mutually perpendicular directions. Three mutually perpendicular directions. Okay, three mutually perpendicular directions, such that this is central fingers, C for central finger, that means C for current. This is the central finger. Okay, and so this is C for current. This is the forefinger, F, forefinger, field. Okay, F for forefinger, F for field. This is C for central finger, C for current. So if this is field, this is current, this will be the direction of the force. This will be the direction of the force. So here if you see, this is field. So field is inward. Field is going inward. Current is going in this direction. Current is flowing in this direction. So what is the direction of the force? Force is in the downward direction. So this conductor is experiencing a force in the downward direction. Okay. So using this cross product rule, also you can find the direction of force. Using Fleming's left hand rule, also you can find the direction of force. Whichever method is convenient to you. The point is, the concept should be clear. Okay. Achha. Now I can write this as F is equal to ILB sine theta, where theta is the angle between the direction of the current carrying conductor and the magnetic field. Okay. So as in this case, see in this case current is flowing in this direction. So IL vector, this IL vector, it is in the direction. See, I told you L vector is L vector. How to mark the direction of L vector? That is always in the direction of flow of current. So current is flowing in this direction. So IL is in this direction. B is going inward. So what is the angle between IL and B? It is 90 degree. So here theta is 90 degree. Now obviously when theta is 90 degree, the force will be maximum. So force is maximum and it is equal to ILB. So a current carrying conductor placed in a magnetic field will experience a maximum force when the conductor is placed perpendicular to the direction of magnetic field. When the conductor is placed perpendicular to direction of magnetic field, it is going to experience maximum force. Okay. Now similarly, if theta is equal to 0 degree or 180 degree, if theta is equal to 0 degree or 180 degree, so sine 0 is 0, sine 180 is also 0. So in that case, force will be 0. So that means if this conductor is placed such that the current is flowing in the direction of magnetic field, means magnetic field is either in this direction or in this direction. Okay, means either parallel to the direction of flow of current or anti-parallel to direction of flow of current. In either of the two cases, the force experienced by the conductor will be 0. It is not going to experience any force. Okay. Now another important thing is, see here this L is a vector quantity. L is a vector quantity. Okay. L is a vector quantity. It implies one thing is it is having a direction, and direction is in the direction of flow of current. It is also one important thing, like suppose you have a conductor like a semicircular arc, magnetic field in this region it is inward, this is the direction of the magnetic field. Okay, suppose I am marking the magnetic field at this point, but suppose in this region magnetic field is directed inward. Okay, I am writing it over here, but magnetic field in this region it is directed inward. Okay, and this is a semicircular arc, this radius is R, it is carrying current I. Okay, so see expression for force, it is IL cross B. So this L is a vector quantity. So L is a vector quantity means length when you are measuring from this point to this point, vector, that means shortest path you have to measure. Okay, so that means here this length here L will be equal to twice R. L will be equal to twice R, and magnetic field is directed perpendicular to the plane of the board. Current is flowing in the plane of the board. So that means these two quantities are mutually perpendicular. So in this case, the expression for force will be I times length is twice R into B. So this is the expression for force. Okay. So that is the significance of this quantity L. Another significance of L. Okay. So we have this question based on the concept we have learned now. A straight wire of mass 400 gram and length 2 meter carries a current of 2 ampere. It is suspended in air by uniform magnetic field. What is the magnitude of the magnetic field? See. So next we have this question based on the concept of force on a current carrying conductor in magnetic field. So the question says a straight wire of mass 400 gram and length 2 meter carries a current of 2 ampere. It is suspended in air by uniform magnetic field. What is the magnitude of the magnetic field? Okay, what is the magnitude of the magnetic field? So the important two terms are suspended in air and we have to find the strength of the magnetic field. So suppose this is the wire. Okay, length is given, mass is given. Now it is acted upon by the weight in the downward direction, but it is suspended in air, so that means magnetic force, it is exerting a force in the upward direction. Okay, now just now we have derived the expression for this force FB is equal to ILB sine theta. This is what we have derived. Okay, but the point is, see here direction of magnetic field is not given. Okay, so if in a question direction of magnetic field is not given, then you have to apply the condition for maximum force. That is, this force is maximum when this theta is 90 degree. Theta is 90 degree. So theta is 90 degree means this force, it is equal to ILB. This force is ILB, and we have to find the magnitude of the magnetic field. That means we have to find the value of this B. Okay. Now this is suspended, so we have to apply the condition for equilibrium in vertical direction. So total downward force it is equal to total upward force. Total downward force equal to total upward force. Downward force means weight. So W, it is equal to total upward force. That is this quantity ILB. So B is equal to W by IL. Okay. So B is equal to W. W means weight. Weight is 400 gram. So that is 400 into 10 power minus 3 kg into mg. This is m into g. 10 divided by current. Okay, how much is the strength of the current? Current is 2 ampere. So 2 into, how much is the length of the conductor? This is 2. Okay, so 2, this is gone. So this is 1. So B is equal to, this is 10 power 3. So this is 1 Tesla. So the strength of the magnetic field or magnitude of the magnetic field is 1 Tesla. Okay. So see, formula is known, concept is known, because if it is suspended, that means two forces are balancing each other. So weight is balancing this force. But the main thing is, see, here nothing about the direction is given. When no information is given, you have to consider that this theta is 90 degree, that is condition for maximum force. Now, based on this concept, same concept, let us try one question from Concept of Physics by H.C. Verma. This is question number 18 from the chapter Magnetic Field, page number 231. Okay, question number 18. A wire carrying a current I is kept in XY plane along the curve. So the curve is given, y is equal to a sine 2 pi by lambda into x. So this wire is kept along this curve, okay, in XY plane. So this is x-axis, this is y-axis. Okay, so a sine 2 pi by lambda into x means the curve is like this. So this is x equal to 0, this is x equal to lambda. Okay, now it is given that the magnetic field B exists in z direction. So x-axis, y-axis, this is z-axis. So that means magnetic field is perpendicular to the plane of the board, perpendicular to xy plane. It is directed outward. So that means we have to mark the magnetic field as a dot. Dot means magnetic field is directed outward. Outward means z-axis. Z-axis is towards you. Okay. Now, find the magnitude of the magnetic force on the portion of the wire between x equal to 0 to x equal to lambda. Okay. So, for this, see wire, this is the wire. Okay. So, wire is like this. This is the wire. Let me draw with a different color. So, this is the wire. And this is the wire. So, we have to find the force on this wire from this point to this point. Okay. Now, see, again we have to use this concept. See, F equal to IL cross B. So, I told you this L is a vector quantity. So, since L is a vector quantity, we have to consider the length as the distance from shortest distance from initial position to final position. So, we have to find the force on this portion. This portion means distance has to be measured in the shortest path. So, that means this length. How much is the length from this point to this point? This length is lambda. So, that means this quantity L, it is lambda. Okay. And what is the direction of magnetic field? Magnetic field is perpendicular to the plane of the board. So, that means this here angle between these two terms, these two vector quantities, here angle is theta is equal to 90 degree. That means force is maximum. Magnitude of the force is maximum. Okay. So, force will be I, L is lambda into B. This is the force acting on this portion of the wire. Okay. So, that is what is asked. find the magnitude of the magnetic force on the portion of wire between x equal to 0 and x equal to lambda. Okay, so this concept of L, that is important. Okay, so regarding L, two things are important, like how to mark the direction of L, that is from the direction of current. This L vector is in the direction of flow of current. Okay, and the other thing is this L is the shortest distance between the initial and the final position. Okay, so this wire of this shape, it is placed between these 2 points. Means this wire actually, this goes like this, but we have to find the force between these 2 positions, and it is carrying some current I. Magnetic field is perpendicular to the plane of the board. These informations are given, but the main concept is this L is lambda. Okay, if you don't have this idea about this L, how to take the value of L, this problem becomes very difficult. Okay, so this concept is very important. So another question, this is question number 10. A wire of length L carries a current I along x-axis. Okay, a magnetic field exists which is given as B equal to magnetic field B, it is equal to B naught I cap plus J cap plus K cap Tesla. Current is flowing along x-axis, so this IL vector, so this length is L, so I can write this as IL I cap, because this I cap is because the current is flowing along x-axis. Okay, so this L vector I am representing as Li cap. Okay, so this is IL and this is B, and you have to find the magnitude of the magnetic force. Okay, now force F, it is equal to IL cross B, IL cross B. So this is F is equal to IL means IL I cap. Okay, this is current, so let me write it as capital I. So this is IL I cap cross B. So cross B naught I cap plus B naught J cap plus B naught K cap. Okay, so this is F is equal to, this becomes 0, so this is IL I cross I, this is 0, so this is B naught also, it is taken outside, so I cross J is K cap, this is minus J cap. Okay, so magnitude of this is F, magnitude is B naught IL, this magnitude of this is root 2. Okay, so this is the expression for magnitude of the force. Okay, again this is a simple concept, F equal to IL cross B, the same formula, this formula is used. Okay, but the thing is current is flowing along positive x-axis, so this vector, how to represent this vector, L I cap. Okay, that you need to be careful. So now let us solve one question from the NCERT, that is the exercise problem, page number 169, question number 4.5. So the question says, what is the magnitude of magnetic force per unit length on a wire carrying a current of 8 ampere and making an angle of 30 degree with the direction of uniform magnetic field of 0.15 Tesla. Okay, so suppose this is the wire, okay, and it is carrying current in this direction. Suppose I is the current. Okay, and the wire is making an angle of 30 degree with the direction of uniform magnetic field. So this is the direction of the magnetic field. Suppose this is B and this angle is theta. Okay, so the angle is given, magnetic field value is also given. We are asked to find the magnitude of magnetic force per unit length. So we have to find the value of force per unit length. Okay, this is to find. Now the expression for force on a current carrying conductor, it is F equal to IL cross B. Okay, now I told you this length is a vector quantity and its direction is in the direction of flow of current. Okay, so this L vector, it is in direction of flow of current. Flow of current. Okay, this is very important piece of information. Okay. So here current is flowing in this direction, so that means length will be in this direction. So if we take the magnitude of this quantity, magnitude of this force, it will be ILB sin theta. So basically this theta will be the angle between L and B, and L is in the direction of flow of current. So we are talking about this angle. So this theta is this angle. Okay. So we have to find force per unit length. So magnitude of force per unit length. So from this we have F by L is equal to IB sin theta. Okay. Now here in the question we have how much is the value of current? Current is 8 ampere. So this is 8, I is 8 ampere. The strength of magnetic field is 0.15 Tesla. So 8 into 0.15 into theta is 30 degree. So sin 30 degree. Sin 30 degree. So this is 8 into 0.15 into 1 by 2. So this is 4 times. So that is equal to 0.6 Newton per meter. So the force per unit length will be 0.6 Newton per meter. Okay. So question is easy, but you need to understand this, how to find this value of theta. Okay. So L is in the direction of flow of current. Okay. So this magnetic field is making an angle theta with the direction of the conductor. That means L cross B, this theta term will be 30 degree, this theta. Okay. So I hope this concept is clear.